is integration by substitution. And this is reversing the chain rule. So you remember the chain rule. And we've already done a little bit of reversing chain rule, but only when it was in the form ax plus b, right? Because then the chain rule was just a number, and you had to, like, the chain rule was, oh, you have to multiply by 5. For integration, we've seen we can undo that by dividing by 5. But if the chain rule had a function, where a function comes afterwards, you can't just divide by that function, because then you would get a quotient rule if you checked your derivative. It's the same as your integral. So, how do we know that we need to use integration by substitution? We have to see a function and its derivative in the integral. So we did some of these already. You work backwards. This was a really easy one. You did this in your notes, in your derivative notes. If you had to work backwards, you'd be like, oh, this came right after you learned the chain rule. Can you see a chain rule happen? That the 5 came out in front. You subtracted 1 from the exponent, and then you multiplied by the derivative of the inside. So your original function would have just been y equals 3x squared plus 5x to the 5. And of course, now that we're doing integration, we would add a plus c. But this question doesn't ask you to find all of them. It just asks you to find a function. So it would be perfectly fine not to have the plus c. Or you could write plus 37 if that's the number that you like. And we notice, of course, that the 6x plus 5 is the derivative of the inside function. So the chain rule happens when you have a function inside of another function. That was our rule for the chain rule. So now we are going to look to see if we have a situation where this occurs in an integral. I'm going to uncolor these temporarily and recolor them with you. What we want to do is take out 2 highlighters. If you have 2 different colors of highlighters, or maybe just 2 colors of pens, you can highlight them that way.
Would Mr. Cox's class please go to B1? That's Mr. Cox's class, please go to B1.
So, for the chain rule and derivatives, all you had to have was a function inside of another function. Working backwards for integration by substitution, we have to recognize a function inside of a function, and its derivative has to appear. So in this case, what I'm going to do in the first one is I'm going to notice that the x squared minus 7 is a function inside the power of 4. And I'm also going to notice that the derivative of the yellow appears in the question as well. So one of the skills you're going to have to get good at is, first of all, is there a function inside of another function? And if there is, does its derivative appear? And what makes it a little bit dicey is that the derivative doesn't have to appear perfectly. The derivative just has to appear in its form. So my yellow part here, its derivative appeared perfectly, being 2x. But the derivative of a parabola is a line, so if any line appeared, we probably would have been fine. Second one, do I see a function inside of another function? I see the x squared minus 3x is inside of a cube root. The derivative of an x squared minus 3x is 2x minus 3. It also appears. This will mean we can use integration by substitution, even though we don't know how to do it yet. But we're going to be able to undo the chain rule because of what has occurred. The first two was really easy to see an inside function. Sometimes they're harder to see the inside function. In the third example, we could technically say that the x cubed minus 5x, because it's on the bottom of a fraction, is inside of an exponent of negative 1. Does its derivative show up? Yes. The derivative shows up in the question as well. Fourth one's a little bit easier. The only function that's inside of something else is tan x. The tan x is inside of sine. Does its derivative show up? Do you remember the derivative of tan? Okay, right? Add that to your quadratic formula on your hand if you're not. The derivative of tan is secant squared. So we notice a function inside, and we notice its derivative is present. This will always be the formula or the hint that you should use integration by substitution. Here, ln x is inside the power of 4. So that looks like my inside function. And the derivative of ln x is 1 over x. And sure enough, that shows up in the question as well. Example number 5. Do you see that the sine x is inside of e to the x? And the derivative of sine x is cos x. Next one, the 3e to the x is inside of cos, and its derivative is 3e to the x. And finally, the last one's going to be a little bit of fun. Because you don't really have an inside function. Well, you have 2x that's inside of sine, but you don't have a derivative of x anywhere. Okay? So we're going to find this last one interesting because we could think of this just being inside a power of 1. I mean, it's not technically inside anything, but its derivative does show up, but its derivative doesn't show up perfectly. Because what's the derivative of sine 2x? It would be cos 2x times an extra 2 because it would have a chain rule. And you could also actually think of the original function being cos 2x, because what's the derivative of cos 2x? It's negative sine 2x times 2. So we're going to find out that this last one is going to give us some different options. So what does substitution look like? And sorry, this is on half of the bottom of your page and then the top of the next page. If you have a function inside, I'm going to color code this the same as we coded everything else. If I have a function inside another function, and I notice that its derivative is present, again, we use u, we get the following, okay? You take the inside function, and you make it equal to u. Then you take the derivative of the inside function, and call it du dx. And this is where calculus and integration, there's a little bit of hand waving here, like du dx means the derivative. It means one thing. However, it's been proven mathematically that this works, even though mathematically what I'm about to do should not be allowed. Okay? Mathematically, what I'm about to do is I'm about to say, I'm going to take the derivative and treat it like it's a fraction. It's not a fraction, but I'm going to treat it like it's a fraction. And I'm going to just take this little dx right here and move it to the other side. So I get du by itself. And what that lets me do is it lets me not only change the g prime x dx, it lets me change that all to du. Then we get another fu function. That would be like this. Okay, this is why this is mathematics. Let's use Newton's notation. Does this work with Newton's notation? Let's say you got y prime is equal to 4x. Right? Could you say y is the prime root of 4x by somehow mathematically getting rid of the little prime sign by prime rooting? Is that such a thing? No, it does not exist whatsoever. It's not allowed. Maybe I just created a new notation that will be allowed 100 years from now in math, and everybody would be like, I can't believe 100 years ago they weren't doing prime roots. Right? But we're doing that here. We're taking the derivative and then like, oh, it was a derivative, but now I'm going to treat it like a fraction temporarily and move things around. Mathematically, that's not allowed, but it works, and we're not going to go into a deep proof about why it works. We're just going to be happy that it works and use it to our advantage. Yeah, this, I'm just going to assume my prime thing is an exponent and work with that. Yeah, no, this is not true, but we're able to do it a little bit with our derivatives. And what this is going to do is we're going to take a complicated integral and change it with substitution into a simple integral. And then that simple integral, we're going to be able to evaluate, and then we can substitute back and get our final answer. So we're going to look at some of the examples that we had already. So here we have the integral of x squared minus 7 to the 4 2x. We recognize a function inside of another function, and its derivative is present. So in our setup, we let u equal that inside function. We find the derivative, du dx. And then we get du by itself by multiplying both sides by dx. So this is our setup. Now we can substitute everything from our setup back into the original equation. We still have our integral sign. But instead of the x squared minus 7, I can write u to the exponent 4. And instead of the 2x dx, I can replace that with du. And we've taken a complicated looking integral and changed it into something really simple. U to the 4. So what does this mean? Well, u to the 4 is just add 1 to the exponent, divide by the exponent, plus c. So we just integrated with respect to u instead of integrating with respect to x. And this is an integral that you could probably do in your sleep. Once you've got the integral with respect to u, we could substitute back now and say, well, what was u? U was just x squared minus 7. We can substitute that back, and now we have our final answer. And of course, if you're a little bit unsure, when you get that final answer, you can always take the derivative to check. Right? If I take the derivative of this, my 5 will come out in front and cancel out with the 5 on the bottom. I would get x squared minus 7 to the 4, and then because it's a chain rule, I'd have to multiply by 2x. Perfect. It matches up with what's inside my integral originally, and I know I have it right. Okay, we'll do one more together, and then you're going to do the next couple on your own. So, B. Again, what did we recognize? We recognized the ln x is inside of another function. Its derivative is present. So this seems like something I should use substitution for. I can make u ln x. Take the derivative. Du dx would be 1 over x. Get du by itself. And I get du is x to the minus 1 dx. So I take that setup and I substitute everything back in. Now I have u to the 4 du. Because the u replaced the ln x. The du replaced the x to the minus 1 and the dx. Just to get du, of course, the same integral that we had from before. Substitute back, and you have your final answer. Again, I could take the derivative of my final answer and check, and it works out perfectly to be what was inside the integral to begin with. Right, if you want to check, see if you were able to get it. I'll give you D then. Here's your setup. All right, here's the answer for E. With your substitution, I moved the x cubed minus 5x to the minus 1 up to the top. You could have left it on the bottom and written this as 1 over u. That's fine as well. But then the natural log appears, and it's much easier to see the natural log with substitution than it did originally in the question. And here's the answer for F.